Hi everybody, Mrs. White here. Today we're going to take a closer look at the graphs of the sine and cosine functions, and then also see if we can connect this to something we've thought about earlier this year called transformations, where we take graphs and equations and force them to slide sideways, up and down, to stretch vertically, see if we can make a connection between the graph and the equation. So before we talk about transformations, let's get a little more comfortable with the graphs themselves first for sine and cosine. These are graphs called sinusoids, which are essentially oscillating waves that just continue to repeat themselves forever and ever as we go around and around and around the unit circle infinitely. So let's take a closer look at the sine graph first. I know this is a lot to look at on this picture, but I'll see if I can use the cursor to make it come to life a little more. So when we look at the x-axis, we're talking about the input of the function, and that would always be an angle. When we say sine of something, that input would always be an angle. So notice here the x-axis is angles. They happen to be in radians, getting bigger and bigger and bigger. The output of a trig function is actually, in this case, the height of the triangles, or the y-coordinate on the unit circle, because we're talking sine here, and we've learned that that's what sine is on the unit circle. So if we look here, when I move over to pi over 6, which is 30 degrees along the x-axis, what I really want to do is graph the height of that 30-degree reference angle triangle, which happens to be 1/2. And then when I move up here to pi over 3, which is 60 degrees, again, I'm now here at pi over 3 on the x-axis. The height of the sine curve is just the height of the triangle, or the y-coordinate, when I'm at pi over 3. And then by the time I get up here to pi over 2, which is 90 degrees, my height is the biggest it's ever going to get, which is 1, because this is the unit circle with radius 1. And I can see that right here, it ends up being the peak of that wave when I'm right here. So here's pi over 2, which is 90 degrees, and I see the height of that curve is 1. And now if I move into quadrant 2, my angles are still getting bigger, but I'm actually seeing my triangle heights start to get smaller again. I'm actually getting lower and lower triangles, and so I can see that happening here. These are the quadrant 2 angles, where the angles are getting bigger, I'm moving to the right, but the triangle heights are getting smaller, which is why I see this sine curve come back down. And then as I move into quadrant 3 right here, now my triangle heights actually get negative, and that's what I see happening right here. My curve is going down because the heights are getting bigger and bigger in the negative direction until I hit a height of -1 here at 270 degrees. And now my heights start getting closer and closer to 0 again as I see this curve getting closer and closer to 0 again. And then this would extend forever and ever. I could go around the circle again and again. Now I'm talking angles bigger than 360, so I would continue to move to the right, but I would see that same pattern in the triangle heights, and I would see that curve repeat itself again. So my sine wave starts at 0 because the original height is 0, and then the heights get bigger for a while, then smaller, and then they get negative for a while and come back to 0, and then again repeat forever and ever after that. Okay, so let's look at this another way. Again, let's really try to stay connected here. When we talk about the sine function, the input of a trig function is always an angle, so that's my x-axis, and the output is the sine value, or in other words, the y-coordinate or height of the triangle when I'm at a particular input angle. And maybe it'll help to see this in a table. So we've looked at these special landmark locations on the unit circle. What I've done here is for the output, I've just put the triangle height, or the y-coordinate, at that location. So sine of 30 is 1/2 because that's the y-coordinate, or the height of the triangle, when I'm at 30 degrees. I also could have actually picked up my calculator and just typed sine of 30, and my calculator would have said 0.5, which is the decimal equivalent of that 1/2. When I get to 45 degrees, the height is now root 2 over 2. I also could have typed 45, sine of 45 on my calculator, and I would have gotten 0.707, which is also what you would get if you took the square root of 2 and divided by 2. So I've got both the exact value here that we've been using a lot lately, and then also the decimal value, which might be helpful if I'm going to be plotting points here to see a graph. So now if I just take all of these inputs as my x-coordinate, and then I take all of these decimal outputs as my y-coordinate, I can actually just plot points. So for example, here's the coordinate that when the input is 60 degrees, the output is root 3 over 2, or 0.866, and I have this coordinate here now. And if I do that for all the coordinates in this table, I will see that nice sine wave form where the triangle heights or the y-coordinates get bigger until I hit 90 degrees, then they get smaller until I'm back to a height of 0 at 180, and then the triangle heights get negative in quadrant 3 and in quadrant 4. And then as soon as I cross through 360 and start to go around the circle again, I'm going to see that exact same pattern of triangle heights once again. And I could do that forever and ever. I could even go backward into the negative angles and I would see that same pattern when I go backward around the circle. I want to take just a minute here and introduce two new vocabulary words. The first one is the midline. Hopefully this one's somewhat intuitive right here. It's basically just the center of the graph. Notice that it's perfectly symmetric where I see the graph going equal distances above that line and below that line. It's kind of like that center of equilibrium, and we'll call that the midline. Amplitude is another word used in trig, particularly with sine and cosine graphs, and it's the distance from that midline to either the highest output or the lowest output. And so for the parent trig functions, just good old sine of x and cosine of x, that amplitude is going to be 1 because the distance from the midline to the highest point is 1. In other words, that was just the radius of the circle. So, and then I get -1 because I also went to the bottom of the circle as well. So amplitude, midline, we'll use those words today. Let's take a quick look at the cosine graph. The cosine graph looks very similar to the sine graph, with one exception. The sine graph started at 0 and then increased. The cosine graph actually starts up at 1 and then decreases. And so let's try to make sense of that. For the cosine graph, the input again is an angle. So if I look along my x-axis, I see the angles getting bigger and bigger and bigger. They would get negative if I move to the left. But my outputs this time are the x-coordinate on the unit circle, or in other words, the length of the base of that special triangle that we can draw. And so if we think about the cosine graph, when we're at 0 degrees, I'm actually over at 1 already. The base is 1. And when I moved to 30 degrees, that was the biggest of all the bases, the √3/2 or the 0.866. And so if I picture that I'm talking the triangle base this time, or the x-coordinate, right away the x-coordinate's 1. But then as I move toward 90 degrees, the x-coordinates start getting smaller and smaller and smaller until I get to 90 degrees. And now the x-coordinate is 0 because I haven't moved left or right. And then as I move into quadrant 2, my x-coordinates get negative for a while. In quadrant 3, the x-coordinates are still negative. And then when I get back to quadrant 4, I'm back to having positive x-coordinates again until I get back to 360. So cosine looks a lot like sine. It just starts at a different place. And the behavior is a little different. So let's take a minute to summarize that, kind of think of this as a checkpoint from where we are with graphs. If I were to ask you to describe any similarities and differences between the parent graphs of y equals sine of x and y equals cosine of x, let's see what we can come up with. Okay, so starting with some similarities, and I'm going to scroll back to the graph here as we talk about these. We could describe both graphs as cyclical or periodic. They're graphs that do something and then they just keep repeating that same behavior forever and ever over time. Okay, sine did the same thing. Both graphs have an amplitude of 1. In other words, for the parent function, if 0 is our center, they go up to 1 and down to -1. In other words, you could think of it as having a range that goes from -1 to 1. They also both extend infinitely in both directions. The domain is infinite. Angles can be as big as we want them to be. Angles can also be negative. Angles can be anything. All right, let's focus on the differences now, though. So the biggest difference is where they start and what they do from there. So if we go back to the sine graph, sine starts at 0 and increases. And again, that was because when we're at 0 degrees, the height is 0, and then the y values increase as we head toward 90. But cosine actually starts at 1 because when we're talking about 0 degrees, the x-coordinate is 1. But then as we start to move around the circle, the x values start getting smaller and smaller. And so cosine starts at 1 and then decreases, whereas sine started at 0 and increased. That's the biggest difference, is just recognizing the difference between those parent functions. But they sure are similar in a lot of ways. So our real goal for today now is going to be, can we take this parent function and can we do things like shift the graph up and down? Or can we actually stretch it so that the peaks get higher and the valleys get lower? And what would cause that to happen? And the good news is it's actually the exact same answer as what we've seen before when we, for example, studied parabolas. So let's take a quick minute to review how parabolas worked here. And then I think you'll be pleased to see that the answer is exactly the same for trig functions. So let's take a look here at this black graph right here, y equals x squared. That's the parent function that we've seen in the past is the shape called a parabola. And now let's focus on the difference when we look at this green one here. Okay, notice that the only change is that this vertex that used to be at 0 is now 2 units higher up at 2. And it actually turns out that every point on the graph moved up 2. This coordinate was over 1 up 1, but it's now at 3. This coordinate here was at 4, it's now at 6. Every coordinate on the graph moved 2 higher. In other words, we shifted it up 2. And what we saw when we studied parabolas is that in the equation, we would expect to see a plus 2 after the x squared, and that alone would add 2 to all the outputs and slide the graph 2 up the y-axis. Okay, so we'll keep that in mind as we think about sine and cosine today. A plus 2 at the end shifts the graph up 2. Let's look at another transformation that we've seen in the past. This graph right here did not shift up or down at all. It's still sitting right at 0, 0 for the vertex. But look at the acceleration of this graph compared to this one. It's growing more quickly. And if we look more closely, we can see that this graph was over 1 up 1, but the green graph is over 1 up 2. It's like we went up twice as far as the original one. And we can look over here at another point and see that same behavior. In this one, when I was 2 units to the right of the vertex, the y-coordinate was up at 4. But now when I look at the green graph, the y-coordinate's up at 8, which is double the original output. And what we saw when we studied parabolas is that putting a multiplier of 2 out front, that was that a value that we called it, that multiplier of 2 is literally what multiplies all the outputs to be twice as big as what they're supposed to be. And we call that a vertical stretch. Okay, let's look at one more that's kind of a combination here before we get back to sine and cosine. So here's one where a couple of things are going on. I've got this original parabola here, y equals x squared. One thing to notice is that the vertex slid 2 units down the y-axis, which we can see right here with a minus 2 at the end of the equation. And then the other big change is that the parabola has flipped upside down. It's like we took the original parabola and reflected it upside down over the x-axis before we slid it down too. And what we saw when we studied parabolas is that a negative a value is what causes that to happen. So almost like a multiplier of -1. It turns the original positive outputs to become negative instead. So let's take a minute and generalize what we're seeing here and see if we can connect it to sine and cosine graphs. When we talk about quadratics, we've seen that the number at the end, the k value, is a vertical shift that slides the graph up and down the y-axis, and that the a value out front either stretches or compresses the graph vertically. And again, if it's ever negative, that's going to reflect or flip the graph upside down. When we talk about trig functions, the good news is that the a and the k value do exactly the same thing. And it's actually true for any function, no matter what shape the original graph is. If we put a number at the beginning, it will always vertically stretch or compress the graph. And if we add or subtract something to the end, it will always shift the graph up and down the y-axis. So let's take a look at a specific example and try to use a little bit of our new vocabulary along the way. Let's say I take this equation right here, y equals 3 times the sine of x plus 1. So let's start with this plus 1 at the end. That's our vertical shift. And so let's think about that midline that used to be at 0 for a sine or cosine graph. That line is going to shift up to 1. So y equals 1 is going to be the new center of the graph by the time we're done. And then 3 is going to stretch the graph vertically. So instead of the graph going 1 higher and 1 lower than the midline, like a normal sine and cosine graph, this graph is going to go 3 higher than the midline and 3 lower than the midline because we're multiplying all the outputs by 3. And notice the peak is still at 90 degrees or pi over 2, just like it was on the original sine graph. And the valley or the lowest point is still at 270 degrees or 3 pi over 2, like it was on the original sine graph. Let's take a look at a couple more specific examples just to make this start to flow a little more. So what I'm going to do is give you a few graphs here, and we want to think about what is that 4 going to do to the parent function, and then let's see if we can actually make it come to life on the graph. So 4 right here is a vertical stretch, or in other words, we can say that the amplitude is 4. Notice there's nothing being added to the end, so the midline will remain at 0 this time. All I have to do is take my original sine graph, which is what you see in green. It's the graph that starts at 0 and heads up to 1 by the time we get to 90. And we're actually just going to take all those peaks and valleys and make them be 4 times as high as they used to be. So anywhere that the graph originally equaled 0, all these zeros or x-intercepts are going to stay that way, because 0 times 4 is still 0. But the peaks that used to be at 1 are now going to be at 1 times 4, which is 4. And the valleys that used to be at -1 are now going to be at -1 times 4, or -4. So we see the graph going up to 4 and down to -4 and still being centered at 0. Let's look at a cosine graph. So notice here, this is the cosine graph, a little different than sine because it starts at 1 and decreases. But I can really still use that as a starting point and now shift. In this case, notice that the amplitude's not changing. It's still going to be 1, but I am shifting the graph up 3. So maybe I should start by taking the original midline, which used to be at 0, and shift it up 3. So now I see a new midline up at 3. It's almost like a new x-axis, but it's actually the line y equals 3. And now the original graph went up to 1 and down to -1 from that midline. I'm going to do the same thing here. I'm going to go 1 higher and 1 lower. It's still an amplitude of 1, but I'm now oscillating around the line y equals 3 because of that shift. And then let's look at one more that's kind of a combination of the two. You'll notice I actually did this one in 2 steps. The pink one here is the final result. So this one right here has a negative sign out front, which is going to flip or reflect the graph upside down. And that's what I did in blue right here. I just took the original sine graph that starts at 0 and heads up, and I literally just flipped the thing upside down. So now the old valley becomes a peak, the old peak becomes a valley. I'm just flipping that graph upside down. But this graph is also shifted down too. So after I've flipped the graph upside down, I should also take the original midline and slide it down too, and also take all of the key points on the graph, which I would include like the zeros and the peaks and the valleys. Just take all those points and slide them down too. And now we have the actual graph of y equals negative sine of x minus 2, which would be this pink one right here. Okay, in today's work, you'll get a chance to try some of this on your own. Let's just do a couple more problems where we try to go backward. If I were to give you an equation, if I were to give you some information about the graph, would you be able to piece the equation together? So let's give that a try here. Let's suppose I tell you that the graph of y equals sine of x has been shifted 18 units up. Well, that would mean that you could write the equation. There's our parent function, y equals sine of x. I'm just going to put a plus 18 at the end, and now I have the new equation. So we're really just trying to make that connection between the shifting or the stretching that we see on the graph and then how the equation looks in its structure. Here's another one right here. We're starting with the same parent function, y equals sine of x, but now we're saying that the amplitude is now 21. Well, the original amplitude is 1. If the amplitude becomes 21, I must have multiplied all my outputs by 21, making it taller and steeper than it used to be. So 21 would be that multiplier out front. Here's one that's a little bit harder, a couple reasons. One, it's a combination of 2 changes, but it's also given to you in a more interesting way. So this time I'm telling you that the graph has been shifted down 3 units, and then I'm giving you the maximum output and the minimum output, which is really that peak and valley that I see on the graph. And I thought in this one it might be helpful to draw a picture so that my brain can visualize what this information is trying to tell me. So the graph is shifted down 3, so I drew a midline at -3. I'm told that the highest it goes is 1, so I put a dot up here, 1 above the x-axis, up at 1, and another one down at -7. And now I can really see my amplitude. If the midline was at -3 and I go up to 1, that's a distance of 4. And same thing here, that's a distance of 4 to get down to -7. So now I know not only that my graph was shifted down 3, but I also know that the amplitude was 4. That's basically half the distance between that high and low. And now I can write my equation, y equals 4 times the sine of x minus 3. Thanks for listening.